Hey everybody, it's Jonathan Broadwell, creator of the Serial Wombat open source project and a embedded systems consultant at my company, Broadwell Consulting Incorporated. So, as you guys may remember, I've been working with a DIY more 6 degree of freedom metallic servo-based robot arm. If you look up above, there's a playlist, or if you look in the comments, that talks about all of the things that we've done with that arm. I was on AliExpress the other day, and I saw for $18 a 6 degree of freedom robot arm that included the servos. You add the shipping and you're still under 24 bucks. So I thought to myself, how good can a $23 servo based robot arm be? Is it worth it? And so this video, we're going to walk through the construction of this thing and try it out and try to answer that question. Is it worth it? This video is going to be pretty long. I wanted to do that on purpose to show you kind of every step along the way, along with the various things like having to deburr the 3D printed parts and those sort of things. These are cheap SLAs that come in the kit. I wanted you to see kind of the whole experience of putting this together. So if you're considering using something like this for a class or just buying one for yourself, you have some idea of what you're really getting into. And hopefully the real-time assembly will allow you to work along with me if you're using this as a tutorial for a robot arm that you've already bought. So I want to take a minute and just plug how I control these robot arms. First of all, I have the Serial Wombat 18AB chip. And that chip is an I2C device that hooks up to your Arduino or Raspberry Pi or MicroPython device and generates the servo signals. It's also capable of doing a lot of complicated control like PID or limiting the rate of change of the servos. So again, look at the DIY more playlist for more information about that. Second, we need a way to power these servos, and these are very small servos. We're going to run these just off of a USB battery, and on Amazon I sell this particular board that is designed specifically to provide power to servos from USB. There's a more powerful one that's designed to take wires from a power supply that's also available, but and then it breaks out the signal line into a convenient set of pins that then we can hook up to the Serial Wombat board or the Raspberry Pi or the Arduino or MicroPython board or whatever it is that's generating your servo outputs. So I'd highly advise you to take a look at those. I really love the product. This is something I've been working on for 5 years. Really love the Serial Wombat chip for driving servos either from your PC or from an Arduino. So before we get started, let's talk about 3 fundamental rules of putting together a robot arm like this. Rule number 1, position your servos before you put them together. Otherwise, you're going to find out that you put your robot together in a way where the servo's already one way or the other. You don't get your full range of motion. Number 2, think before you act. Robots that are based on plastic, you get a finite number of times putting those screws in and out before you wreck the holes. So think twice, screw once, otherwise you may wear out the holes in your plastic. And rule number 3, don't push the robot arm. So you may be tempted to see, oh, this servo, is it moving? Do I have my full range of motion? That may work for little things like twisting the wrist, but if you take and you try to torque the shoulder, that one all the way at the bottom of the robot arm that you see now, there's a good chance that you're going to break the gears inside of the servo. You're going to want to hand torque these things. Don't do it. Put power on them. Let the servo torque itself. Otherwise, you may break your servos. So those are the 3 most important rules for building this robot. So now let's dive right in. So let's take a look at the tools we're going to use. First, we need a way to position the servos. We're going to use a Serial Wombat 18AB chip that's hooked up to a PC. And this board that I sell on Amazon, which is a servo breakout board with USB power. We're going to power that off of a USB battery so that we can position the servos to the center position and test them before we assemble them. Second, you'll want a power drill. As we said before, some of these are very cheaply made SLA parts, and in order to get a perfect fit, you may have to drill out some of the nasties that are left after the printing process. A pair of tweezers is really nice. Some of the cases you're going to have to be able to put a screw in a hole and put a screwdriver on it. These tweezers will help with that. a screwdriver for putting the screws in. That one came with the kit in my case. And a pair of pliers that you can use to push nuts down. Some of the nuts are friction fit into the parts. They use those instead of threaded like brass fittings. And so we'll use the pliers to put pressure on those. So the kit includes all of these SLA printed parts that make up the robot arm itself. Probably the coolest part of the kit is this set of bearings for the shoulder rotation. That's higher quality than what I would have expected. 6 of these SG90 servos. And these are good cheap servos, but in one case we're going to want to make a substitution. We'll talk about that shortly. So not bad for $18 plus $6 worth of shipping. Okay, so let's put together the rotational base. We're going to need one of these servos. And as we said before, we're going to want to position this in the center. So in order to do that, I'm going to use my serial Wombat chip. So this servo is connected up to pin number 12. We're going to go to servo, configure, and that should put us in the middle. And I will power up our battery here, and we hear the servo move. Now each of these servos we're going to want to test to make sure they work. These servos are notorious for not working right out of the bag. If I drag this one back and forth, I'm getting good motion, so it works. I'm going to put it back to 32,768. Yep, 32,768. And so now I know that this particular servo is centered. We will take the base pieces out. And we have these 2 pieces plus the bearings. One of the things we're going to be very concerned about is wire management and trying to make intelligent decisions if we have 2 ways we can put the robot together in how we're going to want that to work. And in this case, let's run all of the wires out of what we will call the left side. And so I'm going to orient this towards my left and just work the servo in there. It's a little hard because of the cable, but I did it before on the sample I assembled previously. All right, so that's popped in. Pretty straightforward. We'll take the 2 screws that come with the servo kit. The long screws are the ones that secure the servo to whatever you're putting it in. They have like a little washer type flange on them. Then we'll put one of these rings in here. I found on the previous sample that there was only room for 1 ring, not 2. And so, see how that fits on there? Okay, we need 2 on this one. And we know that the servo is currently centered, and we want centered to be in that position. So now we're going to take the servo horn, and it uses the horn because these are molded nylon parts that are much tougher than the non-molded SLA parts. And again, this hole is a little bit too small. I found that with the previous one. So I'm going to just hit it real quick and bore it out a little bit with my power drill. And there we go. We got that to pop in. So now we're going to put that on the servo. And we got a good pop there. I can feel it. It's secured. Don't push the servo back and forth. You can break them. And it is binding. That looks good. So let's put the screw in there to hold it. Okay, next we're going to take a look at the shoulder. The shoulder is by far the most torque of any of the servos that we're going to produce. And I actually broke one of my SG90s on the first example of this I put together before this video. I'm going to make a part substitution, and just for this one servo, just for the shoulder, I'm going to change out to an MG90 metal geared servo. Because the weak point in this assembly, one of the two weak points, I believe, is the gears on the shoulder. Because that robot arm can get moving fast enough that when you try to stop it, it has enough inertia that it breaks the gears inside that little servo. So we're going to swap that out for a metal SG90, MG90. And as before, we'll make sure that this servo is fully functional and set to its middle position. Seems functional, 32,768 for the middle. Okay, that's set back to the middle. And we can unplug that. And for this particular part, we have a number of these extensions that are all the same. We have 3 of these. Double checking, you can see they all match up, same part. So we'll use one of those. Bag, there are a number of these screws. In this particular case, with this base, for whatever reason, it didn't want to, doesn't seem to be a good place for a nut. Maybe I'm putting it together wrong. Don't feel too bad about that. I'm pretty proud that I got it together at all with the lack of instructions. So for this case, we're just going to put this nut in here. I'm sorry, this screw in here, and that will act as an axle for this particular part. So that'll be like that. The servo horn goes on the outside, and that's what provides the torque to the arm. I don't know if it makes any difference, but we'll use the black parts that came with the SG90, the MG90. That's going to be a tight fit. I'm going to just scrape it out a little bit, get rid of any burrs that may be on there. And I will use my pliers to put just a little bit of force on that and pop it into place. All right, so I got a good tight fit there. The servo fits in this position, and we can see it'll hold that screw in place over there. Pretty good, clever little design. And so we will, since we adjusted it to its center position, we'll want this pointed straight up. So I'm going to take the servo out, push it into the servo horn in a straight up position, and then pop this. We'll flex it a little bit, get it to go over that bolt. Oh, and I forgot the most important part. Well, not the most important, but an important part. We have one little screw that we need to secure the servo to its position, and that's where we're going to use these handy dandy tweezers. And I didn't get it in there quite straight. That's 32,768, which is the middle point. So I'm going to remove the servo horn. now I'm going to put the arm up to perfectly straight and push the horn in again. And that should have it calibrated to center pretty good. All right, that's better. Try that one more time. Pretty cool. All right, let's move on to the elbow. So now we're going to take another one of our little SG90s. And this works pretty much just the same as before. The only difference is that we will end up using nuts on the assembly. So in this case, the first thing I'm going to do is take and put a nut in this hole. The top hole, the bottom hole is just to get your screwdriver through. And press fit that in there. We will take and put the servo in there. And again, use our tweezers. Next is the wrist servo. And we're going to do the same thing we did before. Make this guy point straight up because we calibrated him to his middle. You're going to pop that over there. That's easy this time because the screw is on the inside. We've got that screw that we pushed into the center. So we're going to take one of the, we have that nut that we pushed into the center. We're going to take one of the screws that came with the kit, put it through this hole and into that press fit nut. We're going to tighten it up, but not too tight, because the more we tighten it, the harder it'll be for that arm to move. So we want it just kind of lightly tight. Tight enough it doesn't jiggle, but not tight enough to put any friction on it. And then we will put the servo horn in here. Probably should have checked this for drill necessity before I put the thing together, but we got lucky. And we will put this in there. And it looks like they actually gave me a spare one of these. So when they kitted it, they gave me too many. That's a lot better than too few. So we actually only need 2 of those 2 parts that go together. Next, we're going to put together the wrist twist. And got some burrs there. We're going to clean those off, make things nice and neat. We'll check to make sure that the servo horn fits in the hole. It does quite easily, actually a little bit loosely. And so in this case, this guy will fit just like that. Pretty straightforward. And again, we will do that in a straight up manner. It comports with the testing we did on the servo. And that looks good to go. Okay, so let's test out what we've got up to this point. I don't have this base secured, so we know that we've added the elbow and the wrist. And there's a lot of friction there. As you move the robot arm back and forth, you'll find that it gets a little bit better. I think what we're doing is probably scraping off some of the texture from those SLAs. As they rub against each other, they smooth up a little bit. And so we'll open another on pin 13 servo so that we can control the wrist at the same time. He really doesn't want to move. And I felt it kind of break loose. Again, it felt to me like those SLAs were kind of binding. Yep. Here, my screw came loose here. Okay, here we have the assembled wrist to wrist twist part. I missed part of that. I didn't have my video turned on, but essentially we did the same thing. We put the horn in here. I had to file this down a little bit. There was too much friction between the SLA parts. They were too rough in order to get smooth motion. And so now that we've got that running, nice motion there. Nice motion there. Ready to go. All right, so now we're gonna finish putting the gripper. I started putting this together, realized my video was off. And so basically there are two gripper parts, one of which fits on the servo horn and one of which doesn't. And you put a screw in this one and a nut on the back, and there you go. So this cleverly, I've set this servo already to the halfway point, and that nut cleverly fits in the non-servo horn part of the servo. So we're going to push those together. And we've got this set in the middle. And so what we're going to do here is assume that middle is about 45 degrees open, which is about like that. Then we will grab the servo horn and put it here. And doesn't really want to bite. The servo going all the way up. This guy's not quite right. I'm going to drill him out just a little bit. I'm hesitant to do that around those gears. Try again with the servo horn. It's a little bit. Okay, and so there we are, fully assembled. So that's installed. I'm a bit worried about these 3D printed gears. They seem like awful fine teeth, and I see a couple of holes in the print. So I don't know that those are going to work out great. But again, I've got an idea that we're going to replace these anyway. So we'll just see what happens. So I'm going to do this. We said we wanted our wire coming out on the left. So we're going to mount this servo this way. Oh, actually, there is a hole for that. So we're going to feed the wire through. And if I had to do over again, I thought that rotation would let me get in there real easy. It doesn't quite. I think we'll get the job done. But I would probably connect up the servo horn after I mounted the servo in the future. And there we go. Looks like a finished robot. So let's hook up all of the channels at one time and see if we can make it grab something. Okay, let's define 6 servos. First on pin 12, we have a gripper. And say OK. And we'll configure that one. We don't need scaling. On 13, we have the twist. We configure that one. On 14, we have the wrist. On 15, we have the elbow. On 16, we have the shoulder. And on 17, we have rotation. Okay. So at this point, they should all be set to the center, which should be a fairly safe place to be. So I'm going to prep this guy to lift him and turn on. Oh, something's not right. And that works pretty good. We're mostly pretty straight up, which I liked it. Okay, so now, if we want to try to grab the evil Skeletor over here, let's start with rotate. Okay, and something stupid happened on our shoulder. Okay. And let's put our elbow down. And let's actually lift the shoulder back up a little bit. Elbow down. Let's put the wrist way down. And let's do a little bit of more rotate. Okay. And let's start closing that gripper a little bit. And we'll drop the wrist a little bit. Drop the shoulder a little bit so that we get closer. And we can see we got problems there because the shoulder can't quite lift. It doesn't quite have enough torque to do the arm at full strength. So it's unlikely we'll be able to lift the model, but we'll give it a try. And let's go ahead and close the gripper. And we'll try and lift on the wrist. And we almost had him. Let's try one more time. We will open up our gripper. And try to we'll just kind of help it out a little bit here. I don't want to spend all day doing this. And close the gripper. And try to lift again with the wrist. And he doesn't quite have enough grip to get that done. So we'll hold him up in the most possible fashion. And if we close around his leg like that, we've actually got him. So can we lift him? Yes, we can. And so let's see if we could put him down someplace else. And we'll drop the shoulder. Open up the gripper. Lift the elbow so that maybe we don't knock him down. And there. Okay, we were able to move Skeletor around with a little bit of help. This is an alternative arm that I created, or an alternative gripper. And what it uses is a linear actuator for its gripping force. And it fits onto the end of the arm that way. But I 3D printed my own custom part. This one's a friction fit that holds the servo in a slightly different manner. So basically, we're just going to unscrew this guy at these points right here and attach the other arm to it. Okay, so here we can see again, I've got the new gripper mounted. This one with its linear actuator has a pretty cool action. It only moves on one side, but I think it should work better for us for our application. So let's see if we can put our shoulder down here. And play with his wrist. Okay, we'll go shoulder up a little bit. Oh, that wasn't right. And one of the screws just fell out of our robot arm. We'll have to put that back here in a minute. And the wrist, can we do that one? And we'll just give him a little bit of help here. And can we close our gripper? Okay, so we've probably got a good grip on his head. And we definitely can lift him quite effectively with that gripper. So we'll, like before, we'll move over here. And we'll gently set him back down. And he's actually on top of that plastic bag right now, so that's not going to work. And the shoulder's having trouble lifting at that long lever arm. So we'll put him down, lift the shoulder some more if we can, to the degree that it can. Up, and we went all the way over. That is a danger, and that's why we have those metal geared servos. Is that may well have broken the plastic geared servos. And we'll do a wrist. And now he's hanging. All right, well, we tried. Anyhow, we clearly have a functional robot that can lift and move things. If we had an automatic kinematics like setup, then we could probably do this much more effectively than me dragging the sliders around. So to answer the question, is it worth it? Yes, it's absolutely worth it. I haven't seen anything that even comes close to this with regard to 6 degrees of freedom. This would be a great robot arm for a kit with students or things like that, or if you just want to start getting around play for a minimal amount of money. I would definitely look at a couple of these robot arms working in conjunction if I wanted to create an animatronic Chuck E. Cheese style move your eyes, move your lips, and have arms that move around without grabbing anything. This particular robot arm has very little grip, and so don't expect to lift anything heavy with it. If you change out the gripper, as we did with the linear actuator, we saw that we can pick up something that weighs a couple of ounces and move it around pretty reliably. And again, I would definitely recommend changing out the shoulder servo for one that has metal gears. And given those caveats, which probably bumps the price up from $23 shipped to $26 shipped, I would say yes, you're not going to find a better beginner entry level servo arm than this. I would highly recommend anybody who hasn't played with arms to play with them. The barrier to entry is exceptionally low, and it's an awful lot of fun for the money. So anyway, until we meet again, have fun, keep making stuff. If you're using the Serial Wombat chip to control a robot arm, please leave a comment down below. Let me know what features you'd like to see, and I'll add them to the firmware if I can. As I said, we've already got motion limiting, we have rate limiting, PID control if you want that. You can see in the videos from the DIY more how to use PID and a current sensor to control grip. So it's quite capable, but I'm always looking for new ideas from users of new functionality that would be good for the Serial Wombat firmware as it continues its motion from being a smart I/O expander to a full-blown embedded systems real-time control coprocessor. Have fun, keep making stuff. The Serial Wombat firmware is available on GitHub and is constantly being updated. Subscribe below so that you can see the latest features and videos that come out as we fix bugs and add new features. The Serial Wombat open source project was created by Broadwell Consulting Incorporated. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Also, feel free to leave your question in the comments below.